This is the new quantum era. I'm your host, Sebastian Hassinger. If you spend any time around quantum hardware, you know there's a layer of the stack that almost nobody outside the field talks about and almost everyone inside the field obsesses over. It sits between the qubits and the software. It's the box, or often a rack of boxes, that take high-level instructions like apply a Hadamard gate to qubit 17 and turns it into precisely shaped microwave pulses delivered with picosecond timing into a dilution refrigerator, and then catches the answer on the way back out, often in a few hundred nanoseconds, fast enough to feed the result into the next decision. That's the way a quantum control stack works for superconducting qubits. There are variations for photonic, trapped ion, and neutral atoms and other modalities, but essentially that's the model. And whether you're building those superconducting qubits, spin qubits, trapped ions, neutral atoms, you cannot live without the control stack. My guest this week is Niels Bultink, co-founder and CEO of Qblox. Niels did his PhD at QuTech in Delft under Leonardo DiCarlo, where he was part of some of the earliest experiments doing real-time feedback on solid-state qubits, a technique that evolved to become mid-circuit measurement, the crux of every quantum error correction experiment that has come after. He started Qblox in 2018, and what's interesting about the company is the shape of how it's grown. About 140 people, more than 150 customers, most of that built on revenue rather than capital. They raised a $26 million Series A only in 2024, which is remarkably late and remarkably small for a deep tech hardware company that already has its boxes installed at places like the Barcelona Supercomputing Center and Quantum Inspire. There's a lot I wanted to get into with Niels. The technical story of why the early IBM quantum experience needed 1 meter of off-the-shelf rack gear per qubit and what had to change. How you actually build a control stack that's qubit agnostic without that being a marketing claim. Why FPGAs might be the right answer today and probably the wrong answer at scale. And then the strategic story. Why the U.S. Department of Energy picked Qblox to manufacture Fermilab's open source QICK platform, a tool that, depending on how you squint, is either complementary or competitive. Why they just spun up manufacturing in Canton, Massachusetts, and what it tells us that the goalposts for breaking RSA have in the last 12 months moved by roughly a factor of 100. We also get into the Dutch question, why this small ecosystem keeps producing hardware companies that scale on customer revenue. I think you'll find Niels refreshingly direct and refreshingly uninterested in hype. This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. Here's my conversation with Niels. Hi, Niels. Thanks for joining me. I really appreciate your time. Tell me a bit about, to start, what was the inspiration for starting Qblox? What was the sort of the origin story of the company?
Yes, hi Sebastian. Great to be here. Thanks for having me. So let me go back a few years indeed. So I founded Qblox 6 years ago, together with one co-founder called Jules van Oven. He's a long friend of mine. We go back about 20 years now. And yeah, I have to say, uh, since I've met this co-founder Jules, we've always been tinkering about starting a company one day. Both going on our individual tracks. Met at university, but going into various businesses individually. So I've been working in the semiconductor industry. He was building sensors for seismic sensors for oil exploration, entirely different fields. But after a couple of years working, I wanted to go back to school. I missed quantum engineering, quantum technology, and I went back for a PhD. So relatively late in my education and career. Also with the mindset of developing a business out of it. So after about 2 years, I was doing very fundamental work on quantum error correction. So making quantum computers that can correct their own errors, and doing the first initial demonstrations of that. And for those demonstrations, we needed new innovative control solutions because quantum error correction by nature means measuring and correcting. So that's a fundamental control problem. So the engineers around at university, but also at the governmental labs here, they were building these sort of prototype control devices to make my research work. And that's where the sort of the initial idea for Qblox sparked. For those, if we need this now for our scientific breakthroughs, the entire field and the development of quantum computing will need these type of control systems to move forward. So it's just using that advantage, sort of that initial head start, and building a company out of it. So that's how we decided to go for it and build Qblox
And that was
run
that
with
was
it.
at TU Delft, right?
Correct. So we're based
Yeah.
in Delft, the Netherlands. Yes, correct.
Yeah. And was that that you went back to get your PhD with the idea of finding sort of a commercial path? Was that inspired by, was Quantum Delta already in existence, or did Quantum Delta happen while you were doing your PhD?
The Quantum Delta as a fund came on a bit later, but we were working in an institute called QuTech that exists, very very pioneering, always top 3, top 5 in terms of scientific output, and they were also very early on in seeing quantum not just as science, but bringing in a lot of engineering disciplines. So microwave engineering, cryogenic engineering to build those next scientific milestones.
Right. Interesting. And so, I mean, what was the, I mean, the in the experimental physics lab, there are, whatever, AWGs and all sorts of control electronics for experiments. And I mean, when you're not talking about a commercial setting, people sort of cobble together control systems out of existing units. What were the limitations that you saw that sort of spurred the need for a custom built, specific qubit control kind of device?
Yeah. No, one of the most funny and typical examples I always find the IBM Quantum Experience. So the first quantum computer that was live in the cloud. So it allowed people for the first time to drag and drop quantum operations on screen and just with a very simple interface control a quantum computer. It becomes funny if you look under the hood, behind the kind of flashy GUI, what for instance, that control stack looked like. So that simple web interface translates into code, and that code translates into programs for these very large scientific equipment pieces. AWGs by companies like Tektronix, Keysight, measurement equipment that is not at all tailored for quantum computing. It was just built for general purpose lab purposes. And that those first quantum experiments and even the IBM quantum experience was built up of those devices, and you would need about 1 meter, so 3 feet per qubit of shelf space, of rack space to control it. So the five qubit computer just had 6 meters of equipment to do it, and Yeah, it's just size, cost, speed of operation, the bugginess of those approaches is it's very easy to see that it's not at all scalable towards the even the systems that we have now with hundreds of quantum bits, but especially if you look ahead where we want to go in the next few years towards tens of thousands of qubits. You really need this hardcore engineering to bring down scale, cost, to manage the complexity and speeds that are needed to make it all work together. That's the
That makes sense. And so, I mean, you performed at QuTech, or what's described as the first sort of feedback on solid state qubits in, I think, 2012. And the Qblox platform is purposefully qubit agnostic. How difficult is it to build a control system that has that sort of agnostic? I mean, in other words, how similar are the different modalities of qubits, or how do you maintain that flexibility?
Yeah, so it's somewhat of a nuanced answer, but it's surprisingly easy to make a control system valid, applicable to many qubit types. And well, if you look at it, especially from the digital side, so the processor architecture that we've built and how it sort of sequences operations, sequences quantum operations, and does measurements. How it relays information throughout the system. That's the bulk of our engineering, the bulk of our IP. That is almost 100% mappable to every qubit type. Where it varies per modality is the frequencies that you need to address them. Some of the qubits operate at microwave frequencies, some of them at optical frequencies. So you need different sort of analog techniques to get from that digital framework towards those qubits. But the bulk of the system really is very widely applicable, and that's also the reason for us to exist in this space, and the greatness of why a value chain is very advantageous to this field. So sometimes companies like us are called picks and shovels. It's a nice analogy, but it doesn't hold entirely. I would more look at it this way: a quantum computer is much more than just qubits, and qubits are the most hard part to develop. But if you look at the stack that is required, the qubits are just the bottom layer of it, and all the other layers of the stack are also crucial to develop. So I think most of the companies and big companies and small companies are really focused on engineering those qubits. But it's very important that those other layers of the stack also reach scale, reach maturity, and that's what companies like us do. And often at those other layers, you can also be much more qubit agnostic. So it's also
Hmm.
advantageous to the field to do it as a value chain. It's much more efficient that we do this for the hundreds of clients that we have instead of everyone doing it themselves. It's just the matter of efficiency for the entire field.
Right. Yeah, that makes sense. And the so what you're saying is across modalities, then it's still very similar to what you described with the IBM quantum experience. It's still classical code that gets translated into a series of signals in whatever frequency range is appropriate for the particular qubits, sent down to the qubits, and then there's sensing or a feedback loop that signal comes back up from the qubits, and you interpret
Mhm.
that and then turn it back into classical data, essentially, right? That's essentially the loop that has to happen continuously.
Yeah. Well, there's quite a apart from the size and the cost perspective, there's quite a fundamental difference of how we have built up quantum control versus how it was back in the day, and that has to do with the rigidity of the system early on. So, what those early systems they would sort of pre-compile the whole quantum program, everything that happens down to the nanoseconds has to be precompiled. So quite memory heavy and slow approach because you have to upload gigabytes of data to your control system for a simple program. So heavy in terms of memory usage, but also slow. And there's no interactivity possible because everything is sort of predetermined, precompiled. If you look at our system and the way we operate qubits, it's much more dynamic. So we have processors that in real time, on the fly, build up these quantum programs, build up these sequences of pulses. And also they can be adaptively programmed. So in real time, at microsecond time scale, measurement information can be used to adapt the control flow. And that sounds maybe like flexible or nice, but that's at the core fundamentals needed for quantum error correction, quantum fault tolerance. It requires you to continuously track errors in the system and correct them, so that sort of flexibility is not just a nice to have or a performance increase, but it's a basic need for this new era of quantum fault tolerance.
And that, I mean, that is critical for, I mean, that speed. If you don't have that speed and responsiveness, then your whatever advantage your qubits are affording you is going to be burnt away by the classical loop for trying to correct it, right? If that's too slow, then there's no point in actually trying to run the quantum computer. So it's a very, very crucial task that you're trying to take on. And is that, I read a bit about the QuTech protocol. Is that part of what allows you to operate at that extremely fast speed?
Yes, indeed. So we have two fundamental protocols, heavily protected, that are very fundamental to our processor architecture. They are called QuTech and LINQ. QuTech is about synchronizing all those processor cores. So we have about one per qubit. So hundreds of these cores currently operate at the same time. And the QuTech protocol allows all those processors to be in sync down to the picosecond even. So there's no, whenever you reboot the system, there are no indeterministic changes in the delays of the signals with respect to each other. And that's quite a difficult but required a trait of the system to be able to scale. The other one is LINQ. That's about the exchange of information between those cores. So how qubit X, the behavior on qubit X can depend on the outcome of qubit Y anywhere in the system. And that bandwidth and speed of how fast any qubit in the system can use information of another qubit, that's very unique in our platform, like how fast and how many qubits you can connect in this way with each other.
And those cores are FPGAs, is that right?
Yeah, the cores, the processor cores, are currently being implemented in our product on FPGAs. So FPGAs is a sort of a flexible logic platform where you can put a signal processing element, or you can even put your own processor core on an FPGA. So that's currently how it's implemented. But yeah, for scalable systems, you will see the field moving away from that paradigm towards more hard-baked processors, because already at the current production volumes that we have, it makes more sense to put things in chips, in ASICs.
In custom silicon. Yeah. That's what I was going to ask. It seems like the FPGA is a very useful platform because of its flexibility, because of its programmability. But in order to get to higher scales, it's very good in this experimental stage of the industry where we're trying to figure out how to tackle these basic challenges of, fidelity, coherence time, error correction, all the rest of it. But I assume that to move forward, you'll have to do something like an ASIC or like your own custom silicon to get that ratio down to, one core per qubit is probably not sustainable when you get to millions of qubits. Hopefully we get to millions of qubits.
Yeah. Working hard on it.
Interesting. Yeah.
But I think exciting times for the field right now, because the goalpost for quantum advantage have moved significantly closer over the past months. So many of the algorithms. One example is Shor's algorithm to break RSA cryptography. A year ago, we thought we would need tens of millions of qubits for that, but the best estimates currently have gone down towards 10,000 to 100,000. So it's really a factor 100 smaller what we now think we need versus a year ago. and those numbers will likely even go down instead of up. So sort of the large pie in the sky that was there the last 3 years has really become within reach right now. That's really exciting times.
That's really cool. So there's three things in recent development of the company that I wanted to talk about. And the first actually is related to that FPGA topic. It's the partnership with the QuickTech team or the QuickTech board out of Fermilab. I've worked with that team before, Gustavo and Show. It's a really interesting platform because it's I describe it as sort of being a Swiss Army knife for a physics lab. It's a FPGA board with a custom I/O board, which they've used for qubit control, but also Gustavo was telling me about a dark matter detection experiment where they multiplexed. I think it was 100,000 or something CCDs detectors for trying to sense dark matter at the bottom of a mine. So it's a really fascinating platform for scientific discovery. I'm curious what the motivation was behind that partnership.
Yeah, no, a good point. So I think a couple of years back when we started the company, it was very much an academic field, almost exclusively. Um, and with the development of the company and the market, we now see sort of a split of that market. A large part of our revenue of our customers are now business to business and are working on scaling up the systems. And the technology needed for that scaling challenge is diverging quite a bit from what platforms you need and want for academic research or even one level earlier workforce education. And for those needs, developing the right workforce and having very flexible platforms even down to the FPGA code. QuickTech has been an amazing system, and it has allowed many people in the field to do things that are not possible with off-the-shelf products like ours. Our products are used a lot in science and help a lot in scientific discovery, also at a small scale, but it doesn't allow some of the flexibility that a platform like QuickTech has. We really like those projects. It is. We really like open source. We have had a strong dedication to open source software already from our inception. We've been doing everything in software open source. So we liked helping that community and that project move forward. Because it has been run from Fermilab, of course, which is kind of a mismatch sometimes because you're doing customer support or support to the field. And for them, it became sort of not maintainable as a project. And for us, it's actually quite synergetic if you look at our current sort of split of the different markets to adopt a project like that.
Yeah, that's really interesting. So in other words, QuickTech would address the sort of the earlier the academic and educational side of the market where sort of ultimate flexibility and openness is actually the most important values, and then the Qblox product line, the rest of the product line would address more the B2B, the commercial applications where robustness and support and specific functionality is really, really important because everybody's trying to scale up. That makes a lot of sense. I love the QuickTech board. It's really an extraordinarily powerful tool for exploration. So I was excited when you guys partnered with them. So that's great. And then along the same lines, the quantum utility block that you launched with Quantware and QControl, that's sort of elements of the supply chain, coming together in an open way. Tell me more about that. That's really fascinating.
So, and it's a great example of demonstrating to the field the value of open architecture of a value chain. So we have, as a company, we supply products, and those products always end up in a stack. And that's in that stack, it connects to software layers above us, it connects to hardware layers below us. And sometimes for our customers, it can be challenging to integrate those different layers, whether they are doing in-house developed software engineering, or whether they're buying products from another vendor for those layers. So what this project is really for is to come together as companies and really work on that integration and understand how can we tailor the products that we have together in such a way that they work better together and to deliver more values to the customer, more performance, but also ease their sort of integration work. And that's, I think, really a great collaboration with these two companies, Quantware, Q-Control, to do that. And also quite successfully in what we have done over the past APS Mars meeting, so the biggest physics event. We have done many demonstrations where we show in a weekend you can actually set up a lab, set up a full stack from zero. And on day 2 of the conference, we could show live performance on qubits. We could actually measure data on those qubits that was used in talks during the same event. So it really is just a nice, really tangible showcase of what you can do with off-the-shelf products rather than inventing things from the ground up.
And commercially, I mean, you described sort of the stack of vendors that, the advantage of Qblox specializing in control systems, instead of customers doing of Qblox is doing that in house. But there is sort of there's a risk in this market to that approach, which is a vertically integrated approach like IBM or Google, or Quantinuum or IonQ. They're trying to build the entire thing in house essentially. Do you see that as just a competitive threat for Qblox, or do you see that as a risk to the market development as a whole?
Um, do I see it as a risk? I would say the trend is quite positive. The trend is more and more companies realize we shouldn't do everything ourselves. And if you look at competitive developments, I would say that the speed at which Qblox develops control stacks and the amount of people and the amount of specialism we can dedicate to it just makes it very hard or not wise for many companies to do it themselves. Makes it much cheaper and easier for those companies to buy from us and to focus on their core IP. If you look at classical computing, it's a huge value chain with so many specialisms everywhere down the stack. The way what we have done to isolate control is just quite a broad layer actually still. So I would actually expect the trend is going to be the other way around, where you will see more and more specialization in different layers of the stack, and the field needs that. That's my opinion.
That's really interesting. So potentially even more, as you said, specialization or fragmentation of the stack from qubits all the way up to the classical interfaces. I mean, it makes sense. If you take the analogy of the classical information technology market, there were early contenders that were vertically integrated from the ground up, but then certainly by the PC era, it was open systems and a richer and richer supply chain with more and more participants. So that's interesting. It's going to be I mean, no matter what, it's going to be very interesting to see how this all evolves. And so, like in terms of evolution, the most recent sort of development for Qblox is expansion into the U.S. Right? It was just earlier this month that your facility in Massachusetts sort of went live, and that's a manufacturing site. What's the significance of a U.S. site to Qblox, and how does that factor into your strategy?
Yeah, so indeed, so we have been serving the American market from day one. So from 6 years ago, we started with institutes like NIST, and many of the national labs started to buy from us. But we also noticed that it was hard to serve those customers in the same way how we can do it here locally in Europe. So that was a reason 2 years ago to start build up a team across North America. And it has been quite successful if you see how fast we could go, how fast we could grow a team and also grow our market share in the field. And for us, a natural next step has always been to produce locally. I think with geopolitical developments, it is seen as very important to be able to service, to be able to support all technology, to be able to produce all technology locally, and that's for us the reason to make that step. So yeah, very a good progress, and this quarter or last quarter we started with our first production batches made in the Boston area.
That's fantastic. That's fantastic. And I guess the next question is basically, you came out of Delft and QuTech. There's a very impressive, but yourself, I mean, Qblox itself has actually been primarily a bootstrap company. You haven't really raised a lot of capital for the footprint you have in the market and the maturity of the product that you have, which is kind of amazing. And you also have a lot of peer companies that also came out of QuTech and Delft. We talked about Quantware already, but there's also Delft Networks, Orange, I think also QFox,
Mhm.
and Delft Single Quantum and Magicware. Is there something? Is there some special ingredient in the Dutch quantum ecosystem that you can pin that to? Like, what is it? What's in the water there? I guess is what I'm asking.
Yeah, good question. I've been asked this a couple of times already, and I think there are some commonalities, some basic threads. So I think for one, there's quite a strong collaborative mindset that's quite deeply embedded in the culture, and you see it reflected in the ecosystem in the Netherlands and Delft specifically. All those companies almost they work with each other. They do joint go-to-markets. They do co-developments, and they really try to understand how can we together grow as an ecosystem. And the word ecosystem is used almost everywhere in the world, but I see less of this synergistic behavior that fits it well. So I think that has been a strong element of the Dutch companies. The other one is um, it fits into it is this more value chain approach. Like most of the companies you mentioned are not full stack companies, but they are building an element of the value chain, and that's also helps in being less venture backed and being a bit more bootstrapped is the ultimate extreme, of course, but being more revenue driven and more customer driven, and that's also very much a commonality in the Dutch landscape.
That's really interesting. And so last question, you kind of have a unique viewpoint because Qblox is qubit agnostic. So if you had to place a bet, what modality do you think will get to sort of commercial advantage, commercial application first?
Hitting
Putting you on the spot.
hitting dangerous terrain there.
Yeah,
Um,
I know. I had to ask though.
no, I think well the field is developing quite a bit, and I think recently all platforms have been progressing very well. I think most notably past 12 months, I think developments in cold atoms have taken quite a flight, where the amount of physical and also even logical qubits have gone up quite quickly. The other one that is really showing a lot of progress is in the spin qubit. So, for decades they started out as the only sort of solid state qubit, and then for decades we're kind of stuck in this two qubit phase. And but over the past year, the progress in those in those spin qubit platforms has gone up immensely, and yeah, they now are close to competing with superconducting qubits in terms of the size of the processor. So also quite interesting to see it develop. But at the same time, superconducting qubit trapped ions are still the most performant platforms, and yeah, have clear rather low risk paths towards these tens of thousands of qubits, because the fact that those goalposts are moving closer by also makes it for superconducting qubits more likely to reach that level of maturity. They're big they're just big in terms of size, but if it's about 10,000 qubits, you can actually reach that quite elegantly.
Yeah. Fascinating. All right. Excellent. Thank you so much, Niels. This has been really interesting. I think what you're doing with Qblox is really fascinating as a pioneer in the field, and I very much look forward to seeing what the future lies for the product line and for the company. So thank you very much.
Thanks a lot, Sebastian. Thanks for having me.
Thanks again to Niels for a really substantive conversation. What's really interesting to me is his framing that adaptive real-time control isn't just a performance feature, it's a precondition for fault tolerance. In that light, the control stack isn't merely supporting infrastructure, it's a critical path technology. And it explains a lot about why the DOE, Fermilab, and a growing list of national labs are paying close attention to who builds these boxes and where. You'll find links in the show notes to Qblox, the Fermilab QICK partnership, and quantum utility block announcement, and also Niels's foundational 2012 feedback control paper, if you want to go deeper on the science. And if you want more conversations like this, long form, technically grounded, and skeptical of hype, sign up for the newsletter at newquantumera.com. This episode is brought to you by Outshift, Cisco's incubation engine. The need for computational power is rapidly increasing in every sector. From drug discovery to material innovation to complex financial modeling, classical systems are reaching their absolute limits. It's time for a paradigm shift. The answer is a scalable quantum network built on open standards and vendor-agnostic architecture. By uniting distributed quantum devices, you unlock limitless computational power. Learn more about the Cisco Universal Quantum Switch at outshift.com. If you got something out of this episode, please subscribe wherever you listen and share with someone who's thinking about how quantum computers actually get built, not just how they're marketed. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era, theme music by OCH. See you next time.